everyone, welcome to Numbers Online School. Today we'll be going through another problem from the East African Math Olympiad in 24. Here's the view of this problem. Compute the value of the expression here. So here we have a sum of square roots, as you can see, and the time goes from 1, 2, 3, up to 40. So there's a total of 40 summands, and we have to compute the entire sum of the expression. So when it comes to computing sums in like Math Olympiads, one of the first things is to try to of course we suspect that we don't have to actually calculate the square root of this number and then compute the entire sum. There has to be some trick involved. So the first trick that you have to look for is to try to express this sum as a telescopic sum. So a telescopic sum is a sum of the form So a telescopic sum is a sum of this form here. So for example, if you have maybe 2 minus 1 plus 3 minus 2 plus 2 squared minus 3 squared and 4 squared minus 3 squared. So you can compute this sum by cancelling out the parts which are from the first and from the next term. So for example here, 2 squared can cancel with negative 2 squared, 3 squared can cancel with negative 4 squared, and then what you're left with is 4 squared and the negative 1 squared. So in this case, we see that this sum here is a telescopic sum because you can simplify the nearby terms by cancelling out the positive and the negative parts, and so in the end what you're left with is that the positive part of the last term and minus the negative part of the first term, because the terms in the middle cancel out by comparing with the respective neighbor summands. So in this case, this is known as a telescopic sum. So our idea is to try to express this sum as a telescopic sum. So what we will do is to write the general term of this expression. So in this case, as you can see, we start with 1, then 2, then 3. So the general term will be of this form. So we start with the square root of n, and in this case we see that we always subtract with half times the square root of. Now as you can see here, the numbers goes from 1 times 3, then 3 times 5, then 5 times 7, then so and so up to 79 times 81. So in this case, it is not hard to see that the products here, because they're all odd integers, can be represented in this form: 2n plus 1. So this is the general term of this expression here, the summands in this sum here. And you can try to confirm that this is indeed the case. So we want to express this as a difference of two consecutive terms in a sequence. So we want to express this as a difference of two consecutive terms in some sequence. So in this case, we will assume that we will first try to simplify this. We can factor out a half from the square root to obtain that this is the same as 2n minus the square root of 2n minus 1 and 2n plus 1. So in this case, you can try to simplify this further. To do this, we'll try to express this as a difference a difference of some two integers. Say for example k and k and l, like that. So in this case, when you square both sides of this expression, what you're left with is a half times this product here, 2n minus the square root of 2n minus 1 and 2n plus 1. And when you square the right hand side, what you will obtain is that k plus l, then minus twice the square root of k times l. So at this point, you can compare this, the right hand side and the left hand side. So in this case, because k and l are positive integers, assume that they are positive integers, and n is obviously a positive integer. So you can compare the rational parts and the irrational parts. So obtain that k plus l equals to half times 2n, which is n, and then the other part, for if you introduce 2 into the square root, you get 4kl is the same as when you introduce the square root of a half into the under root here. What you obtain is 1/4 of 2n minus 1 and 2n plus 1, like that. So in this case, we try to find the values of k and l in terms of n. At this point, there is a lot of ways that you can do this. One of the ways is to try to solve this by quadratics. So in this case, k and l tend to satisfy the equation x squared minus the sum of the roots, which is n x, plus the product of the roots, which is 1/16 times 2n minus 1 times 2n plus 1, like that. So in this case, we can actually try to explicitly find the value of x in terms of n, maybe by using the quadratic formula. So in this case, what you obtain is that x equals to n plus or minus the square root of, now we have b squared, which is n squared, minus 4 times the coefficient of here times the coefficient of here, which is 1/4, so n squared minus 1/4 2n minus 1 to n plus 1, and then all of this we are going to divide by twice the coefficient of the first of the quadratic factor, which is 2. And at this point, you can try to simplify what's inside the square root here, because at this point, this is the sum and this is the difference and this is the sum. So the product here is 4n squared minus 1, and then divided by 4. Then you take n squared, you subtract this factor here. What you remain with is a quarter. So in this case, we have n plus or minus a quarter of this over 2. So what you end up with is that this is same as n/2, n/2 plus or minus 1/4, like that. So in this case, the values of k and l are actually correspond to whether you take a positive or a negative factor here. So for example, you can set k equals to n/2 plus a quarter, and then l can be n/2 minus a quarter, like that. So in this case, you can see that the sum of k and l equals to n, and the product times 4 will be exactly equal to this factor here, a quarter times 2n minus 1 times 2n plus 1. So in this case, When you take k equals to this factor and L equals to this factor, then they clearly satisfy the problem, this equation here that we are trying to compute, so that we can obtain a telescopic sum. So we have managed to find our values for k and L. You can continue to plug it into our original sum. So in this case, the sum of these terms we're computing from n equals to 1 to n equals to 40. And then what we have obtained is that from n equals to 1 to n equals to 40, this sum here is the same as computing the differences between the square root of these two terms, k and L. So we have n over 2 plus a quarter minus n over 2 minus a quarter, like that. Now what is interesting about this this expression is that it is actually a telescopic sum, because when the sequence that we are considering here is the sequence of n over 2 plus a quarter, because when you replace, for example, this inner factor by n plus 1, when you replace this factor by n plus 1 instead of n, you obtain that this expression is the same as n over 2 plus a quarter, which is exactly equal to this term here. So the telescopic sum here will actually be possible by using these terms here as a difference of consecutive terms of the sequence AI, where the terms AI equals to the square root of I over 2 minus 1 over 4. So the first part that we have just did is for motivation for this problem, which is not necessary to include in your solutions for the problem, but I have included them instead of just plugging it into the original sum, so that you can understand where we obtain this, these terms for which the sum is a telescopic sum. So in this case, as we have seen before, whenever we have a telescopic sum like this, maybe I can simplify it a little bit. I can put some illustration. For n equals to 1 here, we have a half plus a quarter, which is a half plus a quarter, sorry, which is 3 over 2 minus 3 over 4 minus 1 over 4. And then the next term will be when n equals to 2. So it is 1 plus a quarter, which is 5 over 4 minus the next term when n equals to 2, which is 1 minus 1 over 4, which is 3 over 4. And so this keeps on going on. You can see that we have odd terms here. We have 1, 3, 3, 5. So the next term will, at this point, you can see the pattern here. Minus 4 over 4. So this goes on until at the end point here, when n equals to 40 here. So it is 20 plus 1 over 4, which is 81 over 4, minus the next term when n equals to 20, 20 minus a quarter, which is 79 over 4. So in this case, you can see that this is clearly a telescopic sum, because this term here will cancel with this term here. So this positive part of the first term, the square root of 3/4 will cancel with the negative part of the second term, which is the same magnitude but different signs. So here it's a plus. I have a plus there. So this term here you cancel with this term here. This term here you cancel with so this one will cancel. This term here will cancel with this term here, and so on until in the end this term here will cancel with the positive part of the second last term. So what you're left with is this first expression here, and the positive part of the last expression. So the negative part of the first expression, and then you have the positive part of the last expression, which is the square root of 81/4 minus the square root of a quarter. Now, of course, this are squares of rational numbers, so this is equal to 9/1 minus, 9/2 minus 1/2, in which case the answer will be equal to 4, 8/2. So this 4 will be our final answer for this question. Congrats to everybody who was able to reach there, and thank you for watching.